Welcome. This is forces and moments caused by real loads, and it's a very nice topic that will actually tell us where those forces that we had acting on the rigid body and couple moments and all that coming to real structures. So thus far we have looked at loads that are single forces acting at points, right? Well, the name that those loads are called, right, are concentrated loads. Right, so that's when you have right, when you have a beam, right, and you have a load, that's a concentrated load. You have a rigid body, and you have this load over here, a concentrated load. So, but right, so for example, if you are thinking of this truck, and this truck is actually crossing through a bridge, each of the tires, right? These tires, each of the wheels place a concentrated load on the bridge. So this is, for example, a source for these concentrated loads to be acting on this beam. And there are another type of common loading. For example, these loads act, right, on a finite length over an area, right? These are known as distributed loads. For example, right here we have the same bridge beam, and we have a bunch of people just standing in there, and we can think of these people, right? We can think of these people as placing, right, as placing a bunch of forces on this beam, right? So we would call this a distributed load, right, over the body. So what loading conditions resemble distributed loads, right? These are very common, right? Gravel in a dump truck, right? So for example, you have a dump truck, right? So let's say horrible drawing, right? So it's filled with gravel, right? So it's a distributed load onto the truck, right? Cars in a bridge, right? Cars in a bridge. So each car, right, would represent a small load. Oil flowing through a pipeline, right? Also fluids have weights, right? Passengers of a ship, sugar in a coffee spoon, right? Leaves in the tarpaulin, and the list goes on. This is a quite common type of loading, right? So one of the things that we will review in this topic, right, is how to express the distributed loads as point loads. The only reason we do this, right, the only reason we do this conversion is because it is easier to deal with a single load than many small loads like this one, right, for certain purposes, right? So the good thing is that using the methods and procedures we have learned, right, and sometimes a little calculus, right, don't be scared, it's easy calculus, we replace a known distributed load as a single force, right, with a particular line of action, right? This will make things very convenient for some calculations, right? For example, this one in which we have a uniform load, right? In this case, is snow, right, acting on this beam, and then we can replace that by a concentrated load, right? One thing that you can notice here is that getting the magnitude, right, getting how much of the point load, that is usually not a problem. For example, take a look. So it says that this is a snow, right? For snow, I am going to use blue. Oh, I have a nice color here, right? So nice blue color, right? This is a snow acting on my beam, right? And it says that it's 5 kilonewtons per meter, right? So every meter of this beam, and I have 4, I am going to have 5 kilonewtons, right? So this, I can think of it as a small rectangle with height equal to 5 kilonewtons per meter, right? And if it has a total of 4 meters, the total load I have is 5 kilonewton per meter times 4 meters equal to 20 kilonewtons. So the concentrated load is going to be equal to 20 kilonewtons, right? And then where would you place, right? Where would you place this load? Would you place it just at half the beam? The point is that these guys are equivalent, right? Or produce equivalent effects. Would you place this 20 kilonewton load onto half of the bridge, so 2 meters? So what do you think? What does your intuition tell you? Would you place it at 3 meters or would you place it at 1 meter? Well, I think most of you would agree with me that if this is a nice rectangle like this, you would place this load at exactly half, of the beam, right? Now, right, keep this in mind, right? Keep this in mind. Now, I want you to think about this case, right? So I have the same beam that we worked on a little bit before. And in this case, the snow piled upon one side more than the other. So, right, the wind blew a bit in this direction, and the snow, right, the snow piled more on this side. And then it reached 8 kilonewtons per meter. And then in this side, it reached 4 kilonewtons per meter. And the question is, how much load do I have, right, on the equivalent system? Well, about the load, right, we can, this is 4 meters. It's in the same way that we did it before, right? We had a rectangle that was 5 kilonewton per meter high and 4 meters long. So the total amount of load is just 5 kilonewtons per meter over 4 meters is equal to 20 kilonewtons, right? So this is the area, right? This is the area of the rectangle, right? The area of the rectangle. So it's in the same way the area of this trapezoid, right? The area of this trapezoid. Now, to get the area of a trapezoid, we can divide it into a triangle and a rectangle, right? Or we can actually apply a formula for a trapezoid, right? For a trapezoid in which this is 8 and this is 4 and this is 4. So an area for a trapezoid is equal to, so it will be the bigger side, right, plus the smaller side times the length, everything divided by 2. So this area is 12 times 4, which is equal to 48 divided by 2, 24 kilonewtons, right? So this is going to be 24 kilonewtons. Now, the question is, do we place it at 2 meters again? Half of the beam? What do you think? What do you think? Now we have more load, right? Now we have more load on this side, and then progressively we have less and less load as we move to the left. So does it make sense to have this? What do you think? Does it make sense to have this load acting right at the middle, right? What does your intuition tell you, right? Remember, we have to have the same effects, as in the original case. I think you would agree with me that most likely we will be looking at having the resultant force, right, a little bit towards the heavy side, right, a little bit towards the heavy side. So in this topic, we will discover how to find this magical distance, right, in which we can have the equivalent forces. That is the purpose of this section, right? Just to learn where these realistic loads come from and how to place them, right? How to place them. And there will be nothing strange. We'll do a little bit of math, but the main point is that it has to make sense, right? We have to place the loads so we achieve the same effects, right? And the good thing is that it will be something reasonable. Once we get the numbers, it will be possible for us to see, you know what, it makes sense, right? that load is a little bit placed towards the heavy side. We'll be able to see the physical side at all times. So more about distributed loads, and then for example here, I mean our beams, right? So this is the 3D side, right? But in 2D, right, we could see this load as, right, just that 2D. No, these things have depth, right? It's load over area, right? But usually what we will be doing is that we will we will drop the three-dimensional case, and we will express these loads per unit length, right? That's the common way of doing it. So you will see always newtons meter, kilonewtons meter, pounds per feet, and all our loads will be given per unit length. In some cases, right, we may be given a function to describe the loads, right? Not only, I mean, simple things as a rectangle, or simple things as a trapezoid, or even a triangle, right? But sometimes they may even give us some sort of variation, right? The load may actually follow a specific equation. And then you know that if we calculate the area in the past for these two shapes, right? Now you see coming, right, now the point in which I will ask you to use a bit of calculus to find the area of that shape. So that's where the calculus will come into position, right? So more a little bit about 3D pieces, right, and expressing those as unidimensional objects with a linear load, right? So how to get the total, right, the magnitude of the resultant force? Well, we use equilibrium, right? We use equilibrium because that's what we are used to, or we are accustomed to do, right? So we're going to use sum of forces in x equal to 0, sum of forces in y equal to 0, and sum of moments at a given point to help us do these calculations, right? In some cases, we'll have to do integration, right? That's where the calculus comes in. So let's get rid of the fear, right? So how do we do integrals? Our integrals will be easy enough to follow, right? Nothing strange like sine of x times x or something strange like that, right? So our load functions usually are nice enough. Our point is not to do a calculus program, right? So realistic loads usually are quite simple, and they are defined by parabolic shapes, right? Parabolic shapes or some other sort of polynomial. But I think it has been a long time since I have seen a complex load or something given by a complex equation. How to do the calculus, right? So in this case, I have a differential, right? I have divided this load into slices, and each slice, right, has a differential element length of dx, right? So this is dx, which means that the force in each slice is df, which is or can be defined as the load, right? Whatever load I have at that location, right? Whatever load I have at that location times dx, right? It's a small rectangle. I'm defining a small rectangle. I'm finding the area in the small rectangle, and I'm finding it as w times dx. Now remember, w, right? W depends on the location, right? Given by that function. So if I am interested in getting the total, right? The total force, right? I have to integrate, right? From 0 to L, right? From 0 to L, right? I have to integrate the different differentials. I have to integrate the differentials of force, which are given by, right, the load at each point, w in x, times dx, right? That's my integral, right, that I have to solve. And usually, as I was mentioning, it will be something simple, usually, right? So you can see it's the effect of the load and times the width of each slice. So nothing strange, right? Nothing strange on how to define the integrals, and that's the formula that we'll be using, right? So the integral can be interpreted as being the total area, right? The total area under the load curve. That's why, right, when we say that the load is actually a rectangle, right, or it's very similar to a rectangle, all what we do, right, if let's say this is 5 meters and this is 3 kilonewton per meter, right, all we have to do is to get the area, right? 3 times 5 equal to 15, right, for example. Or if the load is a triangular load, right, we saw that using calculus, this is 5, this is 2 kilograms per meter, we are just getting the area. So this guy is 2 times 5 divided by 2, right? So this is equal to 5 kilonewtons, right? So what we have to do is just to calculate the area, right? And then we saw that the proof of that is that, right, whatever is in the integral is the area of the load shape. Now we can calculate these loads coming from the load. We can calculate them if we know the area of basic shapes. And usually for this course, right, it's enough to be very good at just identifying any complex shapes in terms of rectangles and triangles, right? Most of the problems will require you to, or are able to, you will be able to tackle them if you just simplify the loads into rectangles and triangles. Now, if you remember, right, we will next be asking where to place the equivalent load, right? So for a rectangle, it's easy, right? It passes through half of it, right? What we call the centroid. So if we call this, right, how they are calling it B, right? This guy is equal to B over 2, right? What about a triangle? Do we remember what's the centroid of a triangle, right? So the load will come actually, if we call the whole base, if we call it B, right? You may remember that this distance is B over 3, and this guy is equal to 2B over 3, right? 2/3 and then 1/3, right? This is the only, these are the results that you have to really keep in mind at all times. For a rectangle is easy, half of the base, right? B over 2, and for a triangle we are at the third, right? 1/3 of the base, right? 1/3 of the base. Another triangle, if we call this B, the centroid of that force, right, the equivalent will be equal to B over 3, right? Always close to the bigger side, right? So these two shapes, you have to really keep them in mind at all times, right? Do you know the areas and centroids for simple geometric shapes? Well, these two you have to, right? You have to memorize them. And for different shapes, we'll provide you with a formula sheet, right, later on. So the next question is the one that we were looking for, right? Where to place the resultant force so we can have the same effect, right? The resultant force gives us an equivalent force, right, that is equivalent to the original distributed load. So we cannot disturb equilibrium, right? We must then find the location of the resultant force to ensure that the system is equivalent or the body feels the same effects. Now, for translation, it's easy, right? We just have to find the area of the triangle, right? So this is 4 meters, so it's 5 times 4 equal to 20 kilonewtons, right? Where to place it, right? Well, the concept we are going to use to define the location is that the moment of the new resultant force about any point must be the same, right? Must be equivalent to the moment of the original old force system about the same point. So wherever I place, right, wherever I change this into a concentrated load, right, the moment I cause with the new load has to be the same moment that I was causing when I have many loads on this shape, right? So I have to create the same moment, and that is what is going to make us able to define the location of these loads. So for example, right, I have here a situation in which I want to find the location of the equivalent load Fr on this arbitrary loading, right? That seems like to be a polynomial or some sort of function, right? What we don't know is the location of the equivalent force, right? So let's actually apply the definition. We have to apply the same concept, right? I have here my differential of force, remember, right? Force times distance, right? Force times the width gives me my differential of force, right? W in x, load in terms of the location, times dx, right? That is equal to my differential of force, right? Such as that the total force is just the integral from 0 to L from the differential of force, right? So this guy here, right? We're going to integrate all the differential of forces, right? And then we are going to, or we can actually calculate, right, the old moment, right? The old moment about point O caused by the original force. Now, the moment caused by the original force, right, is the moment of all the differentials of force with respect to O, right? So if I have that differential of force there, that will be the moment arm, x prime, let's call it, right? And if I had a different, another differential of force, right, such as this one, let's say over here, another differential of force with another, right? So the moment of this slice with respect to O will be equal to the area of this differential of force, right, times the distance to point O, which is the variable of integration, right? As we sweep this shape towards the right, when we integrate, right, we the moment arm is just x, right? Just x. So the old moment about point O from the original force is equal to the sum of all the differentials of force times x, right? Times x. So differential of force is equal to this. That's the differential of force times x, right? And then we can define an integral that looks like this, right? That's rearranging the terms. So this is equal to the old moment about point O. This old moment has to be equal to the moment caused by the new force, right? So I'm going to write here the new moment caused by Fr about point O is just simply Fr times x bar, right? Take a look at x bar, it's over here. Fr times x bar, right, is the new moment, right? And then all we have to do is to make this equal, right? To make this equal to this old moment. So we write here, right? We write here the old moment equal to the new moment. And from that equation, we just have to solve for x bar, right? So once we make the new moment equal to the old moment, right, we just have to solve for x bar, and then x bar follows this definition, which is equal to the old moment divided by Fr. So in a neat equation, we just write that that sum of moments, right, is equal to the old moment, right? The old moment from the distributed system has to be the same as the new moment, right, from the resultant system. So you see here, right, these two is my df, and this is the moment arm, right, which is equal to x, right, the arm, times the area, right? df is an area, right, equal to the force times moment arm, right? We have the same thing in the right hand side and the left hand side. And finally, we can write an equation for x bar, right? For x bar, which is the old moment and divided by the resultant force, which is the area, right? The area underneath the curve, right? So if you have had these concepts in high school, right, you may remember something like this as the definition of centroids, right? The definition of centroids. But what I want you to notice here, right, is that the distance, right, the magical distance x bar, right, it can be very or it's similar to the same distance as we were getting before, right? A moment divided by a force. So moment divided by a force, right? It's the same. Moment divided by a force will give you your distance d, right? So the concept is very, very close, or has an immediate physical sense, right? One question that you may make it dreading right now is if you have to solve integrals. Now this is an interesting question, right? Ask your instructors if you should focus on the calculation of integrals. Usually, your instructor will tell you if this is something that it's an item that is going to be tested in the exam or not, right? Now, the expectation is that all of you have had a bit of calculus in your high school academic background. So this, indeed, if we give you an integral that it's an easy function, the expectation is that you would be able to, that you should be able to answer it, right? So we are not teaching you anything about calculus here, right? So we are going to, let's say, if the function is just, right, the load function is equal to x squared plus 2, let's say, right, that you are able to integrate these sort of functions, right? So, but ask your instructors if you need more guidance about this, right? Now, if you want to avoid the calculus in some type of problems, right? For example, if you don't want to integrate a straight line, right? 5x plus 2, right? For example, this is 2. Well, this is a trapezoid, right? Again, a triangle and a rectangle, right? So you have to have the ability to see if a complex loading function can be broken down into simpler shapes. Because if you can use simpler shapes, it's just the area of the shape and the centroid, right? And then you can actually do it very, very efficiently. But you should know how to do it with calculus too, right? So let's do a few examples, right? For example, the resultant of a distributed load. It says find the magnitude and location of the resultant force due to the loading shown, right? And then the original drawing has a 0.5 in this side, 0.5 kilonewton per meter, and it says 1.5 on that side, right? But I went ahead, right, and distinguish. I can see a triangle and a rectangle right there, right? You almost see it too, I'm sure. So it's 3 meters, 3 meters, and 3 meters, right? So it's 9 meters in total, right? And we have to find that the resultant force and also the location, right? So I see my first shape, I see my second shape, right? Just rewriting just to have more space, right? And then these are the forces from each shape. And I went ahead and marked the location, and I was able to do that because of the simplicity of the shapes, right? For example, for the triangle, right? The triangle. Now the area of the triangle, right? The area of the triangle is just base times the height divided by 2. Now the height, right? If this is 1.5, the entire thing is 1.5 kilonewton meter, and this is 0.5. This is equal to 1, right? So the area of that triangle is base, which is 9 meters, right? Times the height, which is 1 kilonewton per meter, divided by 2, right? This is 4.5 kilonewtons on the triangle, right? On the triangle. So let's see the red one, right? For example, 4.5 kilonewtons. And what about the blue one, right? The blue one is the blue one. Let me just get some color here. The blue one is a rectangle, and the area of it is 9 meters, right? 9 meters times the height of the rectangle, which is 0.5 kilonewtons per meter. So the area of the rectangle is 0.5 times 9 meters, gives me 4.5 kilonewtons, right? Now, the distance of the two, right? The distance of the two. For example, for the triangle, right? Let me just make a bit of... right, cleaning up here, right? Just clean up. Let's see the location of these forces. So, for example, for the triangle, right? The triangle, the centroid, right, is going to be at 1/3 of the base. The base is 9 meters, right? So this distance is going to be 6 meters. 6 meters. And what about the centroid of the small rectangle here? Well, that guy is going to be at half of the rectangle, which is half of 9, 4.5 meters. So I have the location of the two, right? I have the location of the two. Now, the resultant force, right, that green force, is going to be the sum of the rectangle in the triangle, right? And the interesting thing is that we have to find this distance, right? That is the moment arm of the new force. So let's set it up. So the magnitude of that green force, right? It's easy, right? It's just the rectangle plus the triangle, and gives you 9 kilonewtons per meter, right? And what about the position of the force, right? Well, it has to give us the same moment as the two forces. So let's add the moments, right? Let's add moments at point A, right? Let's add moments at point A. So I have clockwise is positive, right? Clockwise is positive. So I have the blue force. I have the blue force doing clockwise rotation about A, so it's positive. So 4.5 times the moment arm, 4.5 meters. And then I have the red force, right, doing clockwise rotation about A. So it is positive 4.5 kilonewtons times 6 meters, right? And that has to be equal to the moment, right? Equal to the moment caused by the green force, which is Fr times, right, which is 9 meters, times the moment arm, which is x bar, right? So the moment of the old system has to be equal to the moment from the new system, and the only unknown here is x bar. So once I do x bar, I get that it's equal to 5.25 meters from point A, and that is the answer, right? So I have 9 kilonewtons applied at 5.25, and that is equivalent to that trapezoidal function, right? What about this one, right? Example 12, right, gives me another system, right? It's complex, right? But you don't have to worry about things that you don't have to worry about, right? We just have to replace this loading, right? This loading by an equivalent force, and we have to find the position of that equivalent force. Now, so I see here two shapes, right? I see two shapes, one rectangle and one triangle, right? And it says here, I don't need to worry about any other force, right? We just have to find the resultant of this force, right? Take a look. There are two forces here in the support. This is one tension from the pulley, right? And there is one inclined force here, right? We don't have to worry about that. We just can focus on the distributed load. So I see one rectangle, one triangle, right? That is the location of the force in the rectangle, right? And then that force is equal to, right? We are told that this is, right? This point is at 8,000 newtons per meter, so this is equal to 8 kilonewtons per meter. So this rectangle is 8 kilonewtons per meter times 5 meters. So 8 kilonewtons per meter times 5 meters gives you 4 kilonewtons. What about the position of this force? Well, it's just half of the base of the rectangle, right? So it's 2.5 meters. What about the triangle, right? So it passes through the centroid of it, which is 1/3 of 5. Let me see if I can have it. 1/3 of 5 here. And what about the magnitude of it? Well, it's just the area. So it's a triangle that has, it looks like this, 8 here and then 5 here. So 5 times 8, 40 divided by 2 gives you 20, right? So we should get that the resultant force is 20 in the triangle, and the location of the force, right, is 5 meters plus 5 divided by 3, right? So that's equal to 20/3, right? 20/3 of meter, right? So that is the distance of that. Now my resultant force is the green force, which is equal to 40 plus 20, that's equal to 60, right? So it's equal to 60. And then the position of the force has to do with the moment. It has to make the same moment as the blue and the red forces produce. So here is the equation, right? The moment coming from the rectangle plus the moment coming from the triangle has to be equal to the moment coming from the resultant force. And then once we plug the numbers into that equation, I get that x bar distance is equal to 3.89 meters. And then after a while, right, it feels, the problems should feel quite similar to each other, right? Quite similar to each other. So with that, we finished this topic in which we learned where the moments and the forces come from in a real situation, and how to reduce them, right? How to get onto a resultant force and the position of the force, so that we can easily handle them, right? So see you on the next topic, in which we will learn how to calculate the reactions, right? So how the beams and the structures in real life react to the application of loads, right? So we have to find how they react to these loads, and what is the value of the forces that real structures generate at the supports. So thank you very much, and see you on the next video.